Thank you very much for the introduction. Can you see my screen now?
Yes.
Perfect. Okay, well, thank you for attending this presentation, of course, in the conference. I will present a research into a numerical framework for the electromechanical analysis of conductive tracks in lightweight embedded electronics. And that research is part of a LEBET, that's an innovation testbed for the development and production of nanomaterials for application in lightweight embedded electronics, and is a cooperation of the Jeroen Krippenberg and supervised by Mark Geers and Joris Remmers at the University of Technology in Eindhoven. So I probably don't need to introduce 3D printed electronics any further, as Martin just did perfectly. So I'll focus a bit more on LEBET and what the project this research is part of is actually doing. So LEBET is an innovation testbed for the development of those nanomaterials that can be applied in lightweight embedded electronics. And I placed a lot of pictures of examples of 3D printed electronics and applications in, for example, antennas or flash drives, but also in healthcare on this slide over here. And LEBET actually tries to tackle the barriers for nanomaterials in lightweight embedded electronics, which are identified as long development times, high cost due to the development and limited volume production, but also the lack of currently digit pilot lines or methodologies and quality standards. So the aim of LEBET is actually to offer this technology for the current European industry, and we'll do that using in 3 phases actually. So there is a techno-economic modeling phase, a pilot project, and a knowledge transfer. And our project is part of that second phase, which I enlarge over here. And in that second phase, we focus on the production of nanomaterials with a couple of partners, the formulation of conductive inks, and the production of components in component pilot lines. And we are actually part of this last element. We're hovering a bit with our research over those 3 components as we try to tackle the challenges that we now observe in the application of nanomaterials in lightweight embedded electronics. And I would like to demonstrate some of those challenges by first introducing a typical process for the creation of the production of embedded electronics. So what you can see here is a already 3D printed substrate in which cavities are left open, electrical components may be placed, and a groove circuit can be printed using the conventional additive manufacturing techniques. And this groove circuit can then in a certain moment be filled with a conductive ink, and the product is then finished. And what we encountered during this single production process is actually some challenges that are mainly caused by the combination of multiple processes and multiple materials in the product. Besides, we are printing on flexible and variable substrate materials, and temperature loading may cause stresses and strains into the conductive tracks during processes and operating of the product. So as you can see on this top figure, for example, in a single product, multiple additive manufacturing processes can be used, but also multiple materials are, of course, in contact with each other. And the key thing what we would like to do in this research is actually to determine the electromechanical performance of the conductive tracks in such a product. And with that, we do this by creating this numerical framework for the electromechanical behavior of those conductive tracks in the products or in the lightweight embedded electronics, with the aim to eventually be able to predict the track performance, so the conductive interconnecting tracks in the product for certain or given ink composition, but also analyze the malfunctioning of certain already available conductive tracks or ink formulations, and eventually come up with improved strategies for printing of the conductive tracks. We can place that actually in a kind of comprehensive overview of the research that we are aiming for. So starting from the process conditions and the ink characteristics, we try to create a certain representative microstructure, which can be done on multiple ways actually. And from this microstructure, we perform a multi-physical analysis based on electrostatics, mechanics, and thermomechanics. And with those results, in terms of resistivity and mechanical properties, we try to well, actually give feedback loop into the process conditions and interact circuits. What we now did was actually mainly focusing on this multi-physical analysis to come up with, and that's what I would like to introduce a bit further in this this talk. And for now, we focused actually mainly on the influence of both electrostatics and mechanics, and thermomechanics is something we'd like to add in future as well. So to introduce the numerical framework to you, so this is typical the scientific numerical framework that we're now currently working on. We can think of a certain conductive track that interconnects two electrical components in in an embedded product. And over that track, a certain electric potential difference is introduced. And if you then load this track with a displacement due to example temperature range or temperature elongation of the tracks, then we can see that cracks may occur in this track, and those cracks will eventually cause the sample to have an increase of the conductive track, to have an increase in resistance with possible malfunctioning of the whole product as a result. So what we would like to do is model this cracking or damage behavior of the conductive tracks in those lightweight embedded electronics. And if we zoom in to the material itself, we can describe it using two fields. So the displacement field of the material U and the electric potential field phi. And those materials can be described, so assume this body is the material of the conductive track, can be described by the mechanical stiffness of the body and the electrical conductivity of the body. And some tractions may be applied or boundary conditions for the electrical field. And if we focus on the mechanical part strictly, so on the mechanical part, we can calculate a certain damage effect due to strains induced on the conductive track. So the strains are actually described by a certain phase field parameter, a damage variable as we call it. And the damage variable is steered or determined using the energy strain function, the strain energy. And it's a diffuse approach, so it means that we approximate a certain crack in the material via a decaying profile of the damage. So at a certain area where the material is fully broken, a damage variable can be found that is equal to 1, and in a certain area where no damage is in the material, damage variable will be equal to 0. And based on the accumulated strain in this certain area, we can actually calculate what this damage variable is in the material. And this decaying profile can be is introduced via a certain length scale parameter, which is material depending. Once we calculated this damage variable, we can feed that back into our mechanical and electrical scheme, and alternating the stiffness and the electrical conductivity by damage degradation function. This means, or the effect of this is actually that we degrade mechanical stiffness in the region where a crack nucleation is observed, and we also degrade the electrical conductivity. As a result of this, we also need to ensure that the crack propagation is irreversible. Once actually certain damage area has occurred, the damage cannot be returned in this area as well. So to ensure this boundary condition, we actually work with a history field, and that history field is then calculated again on the maximum accumulated strain energy in a certain material point. So if that's higher than the previous time step, we change this history field, and a new time step is calculated based on this newly history value. This finite is actually encapsulated in a standard finite element scheme and solved using a staggered incremental procedure. And how we do that is assume that we have a previous time step, all displacements, the electrical potential field, and the damage variables known. We can update the prescribed displacements and the electric potentials for the newly time step, and eventually or possibly also the tractions. And with that, firstly compute the maximum accumulated strain energy in a certain material point, so the history value. That's essentially the coupling between the displacement or the mechanical field and the damage field. And once we calculated that, with that, we can actually calculate the certain damage that has occurred in a certain material point. And once computed damage field, we can actually finally compute the damage degradation functions. And that's essentially the coupling back to the mechanical and the electrical field. With that, we can finally compute also the displacement and the potential field. So with the finite element, well, roughly introduced, I would like to focus a bit more on the application to conductive tensile tests. And for that, we actually need a microstructure to generate. And for now, we focus our research on experimental results. So to illustrate this, the application of conductive inks in embedded electronics is very broad. So there are various types of microstructures and conductive ink formulations possible. And for now, we focus actually on the bonds with nanoparticles, of course, as our LeBet is focusing on that. So we create a microstructure based on a certain SEM or FIB-SEM image of a sintered truck. So this is a FIB-SEM image of a sintered copper ink. And from that, we generated purely for illustration a 2D microstructure. And if we then zoom in on this microstructure and mesh this for a certain finite element simulation, we can apply potential difference over this mesh and load it in strain as well. And with that, I would like to show you the results. So firstly, we can see when the load displacement is increasing, we can see that damage is evolving. So the animation will start over again. You can see that at smaller areas, of course, the stress is increasing and damage will evolve over there. And that has an effect on the mechanical stiffness and the electrical conductivity in the samples as well. That can be seen over here. So here we have an animation of the potential electric field actually over the whole sample. And what you can see is as soon as the damage starts to evolve, there is a distinct transition between the positive and the negative potential as prescribed. So that means that actually no flow of electrons is possible anymore. And that's what we can see in this lowest picture. So of course we see a higher density of electrons in those regions. But as soon as damage evolves, the conductors on the ampere per square meter decreases quite fast, and it results in no, increased resistance or no conductivity for the sample. And that's something we also observed in experiments that we performed on our university before. I can show you this video as well. So what we can see over here is a tensile test of a printed conductive ink. And of course, then the strain increases, cracks are formed in the conductive track here as well. Finally, also the substrate breaks, but we are interested in this time scale actually before failure of the substrate. And what we can see over there is that by an increase of engineering strain, also the resistance, the normalized resistance increases tremendously. And what we would like to know from this research is a point or identify what a certain ink is able to handle for strains before total failure on an electrical field is observed. And in something similar we observed actually in our experiments already. So as soon as the engineering strain is increased, we can see that the normalized resistance goes up till a factor 10 of the original resistance. What we are currently working on is extending this model into a 3D model and validating that using CT scans. So assume we have a certain track. We use a nano CT scan to identify the exact microstructure of a particular zone of this track in which we expect damage to occur. We generate a finite element mesh in 3D of this zone, and we then perform the numerical simulations with the model I just elaborated on for you, and then we compare this with the experimental results of the same track under strains, which we do in a way as shown over in the right, using a 4-point measurement probe. So to conclude, actually, I would like to mention that we just generated a numerical framework for the electromechanical analysis of conductive tracks in lightweight embedded electronics, using a coupled system of equations, and we put it in a finite element implementation. And we are busy with the validation and primary results based on the SEM images, and also trying to validate this model using CT data to the microstructure, from the microstructure of inks. And with this, we hope to be able to predict upfront how a certain ink is able to be applied or to withstand certain strains as occurs in, for example, stretchable electronics, and with that improve also the inks or the ink characteristics that are applied in those products, all to prevent products from failure. So we are doing some in situ conductive tensile tests for the validation, and then I would like to end with thanking the REBAT project, of which this study is part of.